SpaceX rockets land themselves because throwing them away after a single use made space exploration financially impossible, and Elon Musk decided to fix that. This video covers exactly how they pull it off, why it took years of explosions to get right, and what it means for where spaceflight goes from here. For decades, the entire rocket industry operated on what is genuinely one of the most wasteful business models ever devised. Every time a rocket launched, the engines, the fuel tanks, the guidance computers, the structure, virtually the whole vehicle got discarded. It fell into the ocean, burned up on re-entry, or drifted into space, and then engineers built another one from scratch for the next mission. Musk's analogy for this cuts right to it. Imagine if every time a passenger jet flew from London to New York, the airline threw the plane into the ocean on arrival and assembled a brand new one for the return flight. Air travel would cost millions per ticket, almost nobody would fly, and yet that throwaway logic describes exactly how rockets had worked since the beginning of the space age. The numbers explain why this mattered so much. On a Falcon 9, the first stage booster accounts for roughly 60% of the vehicle's total cost, the upper stage another 20%, and the nose fairing another 10%, which means the booster and fairing together represent about 80% of what a launch costs. Under the old model, all of that got thrown away every single time. NASA's Space Launch System still operates that way at an estimated $2 billion per flight. SpaceX's Falcon 9, even before reusability changed the economics, was already advertised at $62 to $67 million per launch, far cheaper than legacy competitors. But SpaceX believed the costs could drop much further if they could just bring the rocket back. SpaceX went public with its reusable launch system concept in September 2011, and the plan, stated plainly, was this. After the first stage booster separates and sends the upper stage and payload toward orbit, instead of letting it fall apart over the ocean, you fly it back, land it on its engines, refuel it, and fly it again. Clean in theory, brutally hard in practice. What most people don't appreciate is the physics of what re-entry actually involves. The booster separates from the rocket at approximately Mach 10, somewhere around 10,000 kilometers per hour, and then has to slow down, turn itself around, navigate back through the atmosphere, and land vertically on its engines, all without a pilot, with no second chances, and on a target that might be floating at sea. SpaceX started with something smaller. In September 2012, tests began with a dedicated prototype called Grasshopper, a suborbital vehicle built purely to practice the landing maneuver at low altitude and speed. And between 2012 and 2013, it completed 8 vertical landings, including a 79-second round-trip flight to 744 meters. By March 2013, SpaceX announced that every subsequent Falcon 9 booster would carry the hardware for powered descent. The first real drone ship attempt came in January 2015, and the booster actually hit the ship, which was already an achievement nobody had managed before, but came down too hard and exploded. The cause was straightforward and infuriating. The hydraulic systems controlling the grid fins ran out of fluid before touchdown. The rocket veered, and that was it. A second attempt in April 2015 ended with the booster toppling over on the deck and exploding, destroying the drone ship beyond repair. Then, in June 2015, a completely separate problem. A Falcon 9 broke apart shortly after launch due to an overpressure event in the upper stage liquid oxygen tank, grounding the entire program for several months. SpaceX fixed it, upgraded the new Falcon 9 full-thrust variant to approximately 30% more performance than its predecessor, and came back. What unfolds during a Falcon 9 landing is a sequence of 3 distinct engine burns, each solving a different part of the same problem, all compressed into roughly 8 minutes from separation to touchdown. First comes the boostback burn, where engines fire to slow the stage down and redirect it toward the landing zone. Next, the entry burn, firing again as the stage hits the denser lower atmosphere to manage the heat and deceleration. And last, the landing burn, where a single central engine, sometimes up to 3 on more demanding missions, ignites in the final seconds to bleed off the remaining velocity just before the legs touch down. The speed numbers here deserve a moment. Coming out of the entry burn, the first stage descends at around 4,700 kilometers per hour, and by the time the legs contact the ground or the deck, that figure has dropped to about 20 kilometers per hour. The whole deceleration sequence runs autonomously, with no human input, directed entirely by the rocket's own computers. The steering through the descent falls to the grid fins, 4 lattice-structured control surfaces that fold out from the top of the first stage moments after separation. Each one measures roughly 1 meter by 1.5 meters, which sounds small for a 14-story structure traveling at hypersonic speed, but they can pitch, roll, and yaw the booster up to 20 degrees, and that's enough to thread a precision landing onto a ship at sea. The original aluminum versions turned out to run close to their temperature limits during re-entry, with some actually catching fire. And that's why June 2017 brought the switch to titanium fins, cast from a single piece, far more durable and never needing replacement between flights. Grid fins, by the way, weren't a SpaceX invention. Soviet scientist Sergei Belotserkovsky led their development in the 1950s, and various Soviet ballistic missile designs had been using them since the 1970s. SpaceX took an existing idea and applied it to a problem nobody had solved before. The flight software runs in C and C++ across a triple redundant computer architecture, where 3 processors each independently assess the situation, compare their conclusions, and only send a command when all 3 agree. Disagreement restarts the process. The drone ships, meanwhile, hold their position autonomously using 4 azimuth thrusters, 1 at each corner of the modified barge, maintaining accuracy to within 3 meters, even in storm conditions, which matters when the landing pad measures 52 by 91 meters and the booster's legs span about 18 meters when deployed. Those drone ships carry names that come from the science fiction novels of Ian M. Banks, specifically from his Culture series book, The Player of Games, published in 1988. Musk named them as a tribute to Banks, who died of cancer in 2013 at 59 years old. Of Course I Still Love You currently operates in the Pacific from the port of Long Beach, while Just Read the Instructions handles Atlantic landings from Port Canaveral. Fuel for a Falcon 9 launch runs between $200,000 and $300,000. That's it. That's what actually gets burned up. The booster itself, that 60% of total vehicle cost, is hardware, and hardware doesn't have to be thrown away. Musk has put the refurbishment cost of a recovered booster at roughly $250,000, close to the cost of the fuel itself, and the total marginal cost of flying a reused Falcon 9, meaning the cost of running one additional mission once all fixed costs are accounted for, sits as low as $15 million in the best case. Christopher Koulouris, SpaceX's director of vehicle integration, put the all-in figure at $28 million. Musk's position on when the economics turn positive is straightforward. SpaceX breaks even on the second flight of any given booster, and from the third flight on, every launch adds to the savings. Compare that to United Launch Alliance's Atlas V at around $160 million per launch, or NASA's Space Launch System at over $2 billion. ULA's own analysis concluded that a booster needs at least 10 flights before reusability pays off, but SpaceX's answer to that argument is booster B1067, which has completed 34 flights as of May 2026. The scale of what this unlocked shows up in the launch cadence numbers. In 2025 alone, SpaceX completed 165 orbital flights, nearly 1 every 2 days, and accounting for approximately 85% of all American orbital launches that year. The company now holds more than 60% of the global commercial launch market. Before reusability became routine, SpaceX was completing fewer than 20 launches per year. By April 19, 2026, the 600th landing of an orbital-class Falcon booster had been recorded, with fairing halves reflown more than 300 times on top of that. Landing on legs looks almost conventional now compared to what SpaceX pulled off on October 13, 2024. Starship, the next-generation system SpaceX is developing for cargo and eventually crewed missions to the Moon and Mars, dispenses with landing legs entirely on its super-heavy booster. Instead, the booster descends back toward the launch tower and gets caught mid-air by two large mechanical arms attached to the structure, a system SpaceX calls Mechazilla, with the arms nicknamed the chopsticks. About 7 minutes after liftoff during Starship's fifth test flight, the 230-foot Super Heavy booster hovered near the tower at Starbase in Boca Chica, Texas. The arms closed and it was done. Mission control went quiet for about half a second before the room erupted. Kate Teese, speaking live during the broadcast, called it a day for the engineering history books, and commentator Dan Hewitt outed that even now, watching it happen in real time, it looks like magic. The reason SpaceX moved away from landing legs on Starship comes down to turnaround time. A booster that lands on legs has to be transported back to the launch mount before it can fly again, and that takes time. A booster caught directly by the launch tower is already in position for its next mission, and that difference is what makes the goal of reusing a Super Heavy within hours rather than weeks actually achievable. Starship version 3 is in active development and testing as of mid-2026, with SpaceX planning the first attempt to catch the Starship upper stage using those same chopstick arms on an upcoming test flight. If the full system reaches operational status, payload costs to orbit are projected at around $10 per kilogram. Falcon 9 currently achieves roughly $2,700 to $3,000 per kilogram. The space shuttle ran about $54,500 per kilogram. A fully reusable Starship delivering on its design intent would represent a reduction in the cost of reaching orbit that the space industry hasn't seen anything close to across its entire history. The premise here is simple, and the answer turns out to be equally direct. SpaceX rockets land themselves because 60 years of throwing them away had made space financially unsustainable, and the only way to change that was to stop discarding the most expensive part of the vehicle after 8 minutes of flight. Getting there required years of work that looked, from the outside, like repeated expensive failures. The first drone ship attempt exploded. The second destroyed the ship. A launch failure in June 2015 grounded the program entirely, and then in December 2015, a Falcon 9 first stage came back down and landed, and the whole calculation shifted. Since then, booster B-1067 has flown 34 times, 600 orbital-class landings have been recorded, and SpaceX has gone from fewer than 20 launches a year to 165 in 2025 alone. The October 2024 chopstick catch of Starship's Super Heavy booster points to where the next step leads. Rockets land themselves because the math demanded it, and what looked like science fiction in 2011 is, in 2026, simply how this is done.